Ooh, what was that? Matt, can you hear us out there? Are we coming through?
Yep.
Excellent. Okay, so just as a reminder, make sure that if you have not sent me a message telling me where you're going to take the test, to do so that I can get those instructions out there. There's also been a question asked of me about grades. This happens every year, essentially, right about this time when we're getting close to the first test. People are worried about their grades and thinking about their grades. And usually it's because I'm not very good at posting grades for things like labs and things. And I often trying to wait for things to happen so I can grade them. I make all kinds of excuses for it, but really I really hate grading. But I will get it done. I think that everybody in both my physics classes now has their lab kits and has at least started the first couple of labs. And so I have started trying to grade them. I usually wait till everybody's first lab is in before I grade the first one, and so on for all the rest of the labs, because I prefer to grade them at the same time and kind of compare people's experiences so that I can see what I can improve and see how people are doing. But pretty much just remember that your grade is based mostly on three things in this class. You have your homework, you have your exams, and you have your labs. It's about 30, 30, 20 for those. And then the remaining 10, 15, 20% or whatever it is that's left is essentially, are you coming to class? Did you take any of the quizzes that we gave? We haven't done many quizzes lately, but if you took the first couple, you're fine. Just stuff like that. It's just random little things. I think it's actually 10% of the class is random little things, and everything else is just, are you participating, completing things, and then exams. So if you've got good homework scores and you're doing the labs, getting those done, you're going to get a decent grade in this class. I don't think I've ever had anybody do those things and get anything less than, I'd certainly not had anybody fail. But most people that get their homework done, and are getting pretty good grades on homework and completing the labs, they're usually getting, at least a B or above. Almost every year when I go through the grades and I look at them and I analyze them, what I see is almost universally people get the same grade in the class that they get on their homework. That is almost universal. And it's not because of the way I've set it up, it's because of the way the class is. If you're doing the homework, you're learning more and you're going to do better on the exams. If you're doing well on the homework, if you're working really hard on it, trying to get it right, asking questions, completing it, getting good grades on it, then you're going to be ready for the exams, and your exams will automatically be pretty good. And of course, if you're completing the labs, that's just extra bonus points, kind of. I don't think the labs are nearly as taxing as homework and exams, and I'm really looking for A, participation in the labs, and B, creativity in learning to use the equipment and trying to learn things on your own, not looking for necessarily the right answers all the time. So anyway, that's where we're at with that. Any other questions about grades or the exam this week before we get started on what we're doing today?
I do have the thing for experiment 3 done, typed up. I just didn't get the chance to turn it in.
I did extend that due date because a couple of different people didn't quite get it turned in on time. So I think
Okay.
it's open. I think that's open for the rest of today to turn in.
Okay, perfect. Thank you.
Yep. Anything else? All right.
Actually, I do have one more question. Well, I guess not a question. With the exam,
Mhm.
I did let the Learning Commons, the one in McCook, know that about the exam coming up Wednesday. I don't know if I sent you an email also talking about that. I don't.
I can check.
Okay.
Well, maybe I can. I don't have my email set up on this computer. Well, maybe I do. There it is. Actually. I do have it set up. Let's see. Yes, you did send me. So that's good.
Okay. Is there anything else I should do other than just let them know that I'm wanting to do the exam there?
Yeah, you just need to make an appointment with them and you're good to go.
Okay, then yep, it's good. It's all set up.
All right. Yeah, I do have this. All right. Okay, so moving on, chapter 5. Chapter 5 is about forces. And one of the classic things that engineers do with forces is build things. And this is one of the most famous things ever built by engineers. It was built about 100 years ago in San Francisco. It's actually between San Francisco and what is called Sausalito. It's a town on the northern peninsula of the Golden Gate. This is my home where I grew up. If you ever have a chance to go to San Francisco, I suggest avoiding anything near the city, except for maybe the city is just a dump, and it's crime ridden too. If you're a tourist there, it's like you have a 1 in 3 chance of being robbed if you're a tourist. Like tourists are being robbed as they pull up to the hotel that they're going to stay in. People will run out and break all the windows in their car and just pull everything out of your car. It's really bad. But anyway, so if I was going to San Francisco, I would stay away from the city and just go visit the surrounding things. So I would go to Sausalito and I would walk across the Golden Gate Bridge. It'll take you to San Francisco, but then you can turn around and walk back. There's actually some pretty cool things at the base of the bridge in San Francisco. You end up in the Golden Gate Park and the Embarcadero area, which is kind of an old army base, Civil War era army base, and they have some cool museums there. In that area, they have actually a submarine, a World War II submarine, which is turned into a museum that's in the water there, and they have the old fort, the old army fort that was a Civil War era fort there, still has its huge cannon in the middle of it. And that's fun to visit. But the Golden Gate Bridge itself is just fun to walk across because they actually have a walkway, a big sidewalk on the side that you can walk on. And you see up close and personal all of the building components of this huge bridge that was built 100 years ago and is still standing today. And it's quite amazing, actually. It's of steel construction, steel towers, steel roadbed, and steel cables, suspension bridge. It's still today one of the longest suspension bridges in the world. So that's pretty amazing. It's one of the longest single span suspension bridges. So it only has one suspension span, which means there's 2 towers and a bridge suspended between them. They did build one much longer in Japan not too long ago, maybe 20 years ago or something like that, 30 years ago. But amazingly enough, the one in Japan is built almost almost the same exact way this one is built. The only difference between this one and the one in Japan really is the length of it, and the towers are so tall on the one in Japan, they're almost like 1,000 feet tall. They're so tall that they actually had to build in some pendulums in the middle to take out, to dampen the vibrations in the towers, because the vibrations in the towers were enough that they could actually pull down the towers. The towers could actually break from the vibrations. So they put some big pendulums in the middle that dampen those vibrations. They move, the pendulums move instead of the tower bending. But still, an engineering marvel, and you can really see it up close when you walk across the Golden Gate Bridge. Really interesting thing you can see here is that the bridge actually has an arc to it. You can see that in this picture, that it has a bit of an arc to it, and it's actually fairly extreme. And that's on purpose. The idea is that the arc actually takes part of the load and transfers it to the towers through the cables, and allows that roadbed to handle more force, more load, has more load capability. And I think it was during the 75th anniversary of the bridge, which was maybe 20 years ago or 10 years ago or something like this. They had a big parade across the bridge and allowed people to walk on the roadbed instead of the sidewalk. But it turns out that people covering the bridge actually is much more load than cars driving across the bridge. And so it actually flattened out the roadbed, and that can be very dangerous. If the roadbed inverts to being concave, it will actually break. Very, very likely will break anyway. So they ended up having to stop the parade and send people off in all directions. Well, in both directions, not in all directions. But anyway, that's a fun thing to go do as an engineer, just as anybody. I think it's just a fun bridge to see. Fun engineering, one of the great engineering marvels of the early 20th century. So we've studied kinematics, the study of motion or the measurement of motion. Actually, kinematics literally means the mathematics of motion. But dynamics is what we're going to study now. And the word dyna, is one of the words from, I think, Greek or Latin or so. I think it's Greek for force. And in fact, there is a unit for force called the dyne. And if you've ever seen people test their grip strength, where they squeeze this thing and it tells them their grip strength, that's called a dynamometer. So dynamics means this. It means the study of, or the mechanics of, force, the things that forces do, the things that forces cause, the measurement of force, the mathematics of force. All of this is included in dynamics, and that's what we're about to start to study. There's actually a subset of dynamics called statics, where the word stat means not moving, and so statics is the study of things that are not moving, but it still considers forces. So the study of a bridge, for example, like the Golden Gate Bridge, would be a study of statics, because the bridge itself doesn't actually move, really. It's not designed to move. It's designed to sit still and handle force load while it's sitting still. Most of what we study when it comes to dynamics and statics are things that were first studied by Isaac Newton. Isaac Newton lived in the mid 1600s, early 1700s, mid to late 1600s, to the early 1700s, which puts him 300 years ago. And it's interesting to think about Newton and other scientists, because the last really game changer scientist that we had in physics was actually Einstein. He came along and really changed the way that we think about physics, and the results of that we see all around us. Pretty much everything in all science and technology that we see today is directly or indirectly a result of things that Einstein did. And before him, the last greatest scientist that really came along and really changed things was Newton. And if you go back through the years, you find that there is a big revolution in science because of really one person who comes along and changes the way we think about science. It's usually one person that makes one really significant, really sublime change in the way we think about nature, the way we understand nature. They come along, they make this change, and then nobody really changes much for the next couple of 300 years. Many is 400 years sometimes. And that's been a pattern that's fairly well established throughout the ages. It really hasn't changed that much. Somebody comes along, changes science, and then we wait 200 or 300 years. Somebody comes along, changes science, we wait a couple of few hundred years. And so we wonder, it's been 100 years since Einstein. You wonder, when is that next one going to come? Is it going to come in 100 years or 200 years? Will it come earlier? A lot of people believe it'll come earlier because a lot of people believe we've made so many more advancements in science and society in general. I'm not sure I believe that, but it's possible. It's possible. People say, but so many more people have access to the information because of the internet. But I actually think that actually hurts intelligence. I think that having information provided to you is damaging to the intelligence of an individual and of society in general. And that's actually why I have you do experiments on your own, make them up yourself. That's why I don't ask you to get a specific answer in your experiments. I want you to do things on your own and be a little bit out there on a limb, not really being told what to do, not really being told what answer you need to get. Because more often than not, the answers that we think are right in science are wrong anyway. More often than not, we find mistakes in our science, or we find problems with the science and we have to change them. But it's only the people that come along and see that actually change science, and it only happens every once in a while. So Newton was one of these great scientists that came along. What did Newton do? It's often misunderstood what Newton did. Here's a nice little painting of Isaac Newton. Isaac Newton was a strange person. Most of these game changers in the world are. Most people who change the game of the human race are really kind of weird people. And we do have somebody on the earth today that I think is a big game changer for the earth. And I think it's Elon Musk. Not that he's not providing new science or anything, but he's really the first person who has looked out into space and said, you know what, we can go there and I'm going to do it. We have a lot of people that have pretended to be that person. And we have a lot of people who have done part of that, particularly people like, you could say people like Wernher von Braun. Wernher von Braun created a lot of the plans and the drawings that Elon Musk uses to do his work in trying to get to Mars. And Wernher von Braun was the head of the space program when we went to the moon. Well, when we went to space for the first time, when we went to the moon, he was not really that involved with it anymore. And Wernher von Braun was originally a rocket scientist in Nazi Germany, and he then was post-World War II. Towards the end of World War II, he kind of split off from the Nazi party and was trying to take his rockets elsewhere. And eventually, when Germany lost, the United States invited him to come to our country to help us with our space program. And the Russians grabbed all the rest of the Germans. And so we had a bunch of Germans and the Russians had a bunch of Germans, and that's what started the space race, because the Germans were the ones that were figuring out how to do rockets during World War II. But anyway, Wernher von Braun had this vision that he wanted to go to space. He wanted to go to Mars. He wanted to go off and even further. But he didn't really have the vision of how to do it economically. He went to the government, which was, the classic thing to do in the 40s. The government, go to the government. Well, Elon Musk has opened up a whole new realm and said, I'm not going to go to the government. I'm just going to do it myself. And now he's had help from the government because he has contracts with the government for his rockets. But he didn't really have help from the government in developing those rockets necessarily. He just started a bunch of businesses like PayPal, Tesla, and used the money from those businesses to pay for his rocket fetish, which is really paying off, it turns out. So anyway, we definitely have somebody who's changing humanity, I think, as we see it right now. He's changing things, and if he ends up getting to Mars, I don't think anybody will dispute what I'm saying in the end. But he's not really changing the way we view science per se. He's not changing our understanding of science much. So that's a completely different thing. Newton did, but how did he do it? Most people think, well, Newton, discovered gravity or figured out gravity, the whole apple falling out of the tree thing, hitting him on the head. And we don't really know if that story has any truth to it or not. And it doesn't really matter because it has really nothing to do with what he actually did, except for it has something to do with gravity, and gravity has something to do with what he did. What Newton did, and he may have actually used the apple analogy or the apple story to explain this to his fellow scientists. Because at that time there was a society of scientists called the Royal Society. Any of you ever heard of the Royal Society? Yeah. So the Royal Society was a bunch of rich people of blue blood or whatever. Blue blood, yeah. Anyway, I don't remember I think they're blue blooded if they're royal. But anyway, in fact, one of my ancestors was in the Royal Society back before Newton was, and these rich, wealthy, royal people would get together and talk science. And they were really the only people that did science back in the day because the only ones have money and time to do it. And Newton was a member of this society. He hardly ever went to the society because he was kind of an introvert and really he was an antisocial kind of person. He much preferred to study and learn rather than talk to people about it. And he didn't like to share his discoveries because he was afraid that people would take credit for them. And he didn't want anybody to take credit for his discoveries. He also studied just a lot of junk, a lot of stuff. He studied astrology and he studied what's that one where they're trying to turn things into gold? Yeah,
Alchemy.
He studied alchemy and he studied spiritualism and he studied ghosts and he studied all kinds of things because Newton truly was trying to show. He was trying to understand as much as he could about the things around him, even if he didn't know the things around him were actually existed, right? So, for example, there were many stories of people seeing ghosts, and he studied that a lot. He was never able to confirm that people had actually seen ghosts or that there was anything that could summon ghosts or spirits like this. He was never able to figure that out. That didn't necessarily mean to him that it just wasn't true, but he was trying to figure out if what people said they observed was real. And that's truly scientific, whether or not, we believe in it or not. It's the science method is to go out and observe things and make measurements and try to understand things. It's not about truth or anything else. It's about trying to understand. It's trying to see, trying to measure, trying to observe. And what he did is he observed science that had been done before him by many other scientists. Some of these scientists, one of these scientists' name was Kepler. Another one was Galileo. Let's see, there's Kepler, Galileo. There was lots of them. Aristophanes. Lots of scientists through the ages had studied the planets. They looked through telescopes at the planets. Tycho Brahe is another one. They'd taken a lot of notes. They'd taken a lot of measurements. They'd made a lot of observations. They'd written down a lot of things, made a lot of drawings. But none of these scientists had really ever figured out why the planets are doing what they're doing. A lot of them had suggested, models for the solar system. A lot of and the universe in general. A lot of people had put together models for the universe that said the Earth was at the center of the universe. Some said the sun is at the center of the universe. Some of them had explanations for why some things in the sky moved and other things didn't move in certain ways, like the stars move very differently than the planets, for example. But nobody had really kind of come together and said, why are they doing this? They'd all have ideas about what was going on, just not why it was going on. And Newton was the one that came along and said, look, the same thing that causes an apple to fall towards the center of the earth, because at that time they were well aware that the earth had a curvature to it. Aristophanes actually was able to prove that with an experiment and others. But so they were very well aware that the earth had curvature to it and was very likely a spherical. They actually knew it because they'd actually traveled around the world at that point. But anyway, they knew this. They knew the earth was a spheroid of sorts. And so he said the very same thing that causes the apple to fall towards the center of the earth is what causes the earth to rotate or to orbit around the sun and all the other planets and the moons in their orbits around the planets and asteroids and comets and everything else. He was the first one to really realize that, to make that connection. And that was huge because that connected something that seemed very grandiose, like the solar system, to something very mundane, like an apple falling out of a tree, right? And it connected them using the same idea, same physics. It's gravity, as he called it, gravity. Later on, that was, well, not even later on, at the same time, Newton also further generalized this to force, that gravity is a kind of push or pull that can cause movement, and that forces existed in other ways other than gravity. There were other kinds of forces. Gravity was one kind of force, but you could also just push somebody, and that was another kind of force. Or pull somebody, and that's another kind of force. So here we have an example of some simple push forces. We have 3 ice skaters pushing, 2 of them pushing the third. Right? One of them is pushing from the right with a certain amount of force in a certain direction. The other one is pushing from the bottom towards the top with a different amount of force in a different direction. And it turns out that forces obey vector laws or vector rules of mathematics, and they are vectors. They have a magnitude, they have a direction, they can be represented by these arrows. And you can add them together like vectors. If you have force 1 and force 2 both pushing on this ice skater and no other forces pushing on this ice skater will feel a force that is the sum of those 2 forces vectorially. We often draw a free body diagram to represent the forces acting on an object. Free body diagrams are designed to make the system that we're looking at more simple so that it's easier to see what's going on with the forces. And we usually represent the system of interest or the body of interest with just a point or a very simple shape, usually just a point to begin with. And then when we get on to more complex things, we use different things, maybe a line or a box or a triangle for our free body diagram. But this free body diagram is just a point that represents the skater in the blue suit. And the 2 forces that are acting on her are the force upward and the force to the right. And we represent the forces as starting at the point where our system of interest is, or our body of interest, and going away from it. So this one here, which came from the left, is actually starting at the skater and pointing to the right. The one that came from below is actually starting at the skater and going upward. And we just draw those 2 forces. Those are the external forces. What do I mean by external forces? Well, the skater herself could lift her arms, for example, and that requires force to lift her arms. But the forces are coming within her body and acting on her body. So they're not going to affect where she is going, where the overall system or the overall skater is going, they're not going to create movement of the skater. They can't create movement of the skater. Now, not all forces, not all external forces cause movement, but external forces can cause movement. And we'll learn more about that later. Other forces that could be included in this free body diagram, that are other external forces that are acting on the skater, include things like gravity is pulling on this skater and pulling her towards the ground. That's what's keeping her on the ice. So we could include that, but we'd have to have a free body diagram that showed that dimension, which we don't have. This free body diagram shows the upward and sideways dimensions as horizontal to the ground, and the gravitational dimension would be into the page in this case, right? So that would be difficult to show in this. It wouldn't be impossible, it would just be difficult, three-dimensional forces. We also might have friction on the ice. The ice might have some friction between her and the ice and the skates, and that might be acting. We don't have that one included, but it could be acting in this case. Friction is a force that is caused by two objects in contact with each other. We'll learn more about it later. So how to draw free body diagrams. We actually talked about that a little bit here, but they have a little 4-step thing you can follow. You can do it any way you want. But the basics is that you want to know what your system of interest is. And then you want to draw all of the individual forces that are external to that system that are acting on that system. So forces that have to come from some other object and act on that system, come from some other source and act on that system. In this case here, we have a block or a box on a horizontal surface. The weight of the box, which pulls it towards the center of the earth, is one external force. It is being caused by the gravitational force, which doesn't require any contact. The two skaters pushing the third skater required contact. They have to actually come in contact with the skater to push. But gravity does not require that. Gravity can act across all of the entire known universe and never touch things that it acts on. That's happening in the universe today. We actually feel the effects of gravity, even though we don't notice them, but we are affected by gravity from objects that are on the opposite side of the universe, that are so far away that their gravitational effect takes the lifetime of the universe to reach us, in fact. So, in fact, might even be longer than that. It might even not reach us yet. So, because gravity actually takes time to exert its influence. Again, something we'll learn more about. We can learn more about later. Yes.
How would you describe gravity as far as like exerting its force on other things? Would you say it's more of a wave or constant?
That's a really good question. And when I figure it out, I'll publish a paper and we'll go to Sweden together and collect the Nobel Prize. There's actually really good evidence. So Einstein's theory of relativity suggested that gravity is a wave, but it's not like any wave that you've ever imagined, that you can ever imagine. When we think of waves in water, or even if we're really crazy, like I grew up in California and I've actually seen a wave travel through the Earth's surface during an earthquake. I actually watched it happen. And it can happen. I mean, the wave, this was in 1989, the big earthquake that happened during the World Series between the Giants and the A's. And that earthquake was so bad that it collapsed part of the Bay Bridge. It collapsed an entire double-decker freeway, killing hundreds of people. It caused all kinds of damage all over the Bay Area that I lived in. But actually, while it was happening, my sister and I were home alone, and we were doing homework in the kitchen, and the earthquake started, and the kitchen is right next to an external door. So we just went out the house, because you're always supposed to either get completely free of a structure or get under something so that you're safe from falling things if you're inside. So we just went outside and we actually watched this wave travel across our yard. And it actually moved our pool. This wave was lifting the ground like inches to feet. Okay, this wave along the surface of the earth. And the wave went through our pool so dramatically. We have a 4-foot deep shallow end and a 7-foot deep end in our swimming pool. And when we were done, we only had a 3-foot deep shallow end in the deep end. 4 feet of the water was gone because that wave created a wave in the pool that literally emptied the pool. So that was something like 25,000 gallons in 3 seconds were removed from our swimming pool. The raspberries got a really good water, on the other hand. 25,000 gallons of water all at once. But we think of waves as moving through physical media, like a wave through a string or something like this. Sound, we often think of as this mysterious wave that just travels through what? It actually travels through air. Sound is compressions and decompressions of air. And air is a thing. It has mass and it has size to the particles. So most of the waves we think is traveling through things. Light waves don't have to travel through things. They can. Light waves can travel through glass and they can travel through other things. They can travel through air. But light waves do not require that. Light waves aren't actually making the air move. They're not making the glass move. Light waves are are energy waves. So it's a movement of energy, which is still something we can kind of think about. Energy, we kind of have a feeling for what it might be, even though it's much more mysterious than what we actually think it is. But we kind of have an intuition we created. It's a false intuition, but it's still an intuition for energy. So we're like, okay, light waves, they're energy. They're waves of energy. Gravitational waves are neither of those things and not even close to either of those things. So gravity waves are similar to light waves in that they travel at the speed of light. They're similar to light waves in that they don't need matter to travel through. They don't have to travel through matter. The difference between gravity waves and light waves, though, is that gravity waves actually require us to think of space and time as a wave medium. In other words, gravity actually puts a wave, it actually distorts space and time. And that's what Einstein said in his theory of general relativity. He said, gravity is a wave that travels through space and space and time, according to Einstein, were essentially the same thing, which has its own whole other connotations. You imagine that time is really just an extension of space, and you're like, what are you talking about? Well, it makes sense if you study it, and I've studied it, but it takes at least 2 or 3 years of physics before you get to that level where you can really wrap your head around it. But it does make sense. And it was proven recently to be true. Actually, we proved it in the 1950s because of an observation that was made during a solar eclipse at that time. But it was even more proven. And nothing is ever fully proven, but we have really compelling evidence, because if gravity behaves like a wave, then we should be able to, like a wave in space and time, we should be able to observe these waves when big gravitational events happen in the universe, okay? But how do you measure space and time being manipulated or being bent or being warped? Well, they figured that out by creating a thing it's called a interferometer. And we've been using interferometers in physics for well over 100 years. We actually use them to discover the speed of light, actually. But this particular interferometer is called a Fabry-Perot interferometer. We actually used it in our laboratory when I was in graduate school. But they're making a really big one, because what a Fabry-Perot interferometer does is it uses light, usually lasers, but it can also use atoms. And what it does is it shoots them in different directions and then bounces them back towards their original source. And when they come back to their original source, the light interferes with itself. The waves come together and the peaks should line up with the peaks if the two paths that you send it down are exactly the same length. The peaks should line up with the peaks, and the troughs of the waves should line up with the troughs, and the light should look just like it did when it left. So you look at it before it leaves, you look at the waves before it leaves, you look at it when it comes back, and it should line up and just be nice, bright light like you're expecting. However, if one of the legs that you send this off, and you send it off in different directions, 90 degrees to each other, if one of those legs is slightly longer than the other, or it gets distorted in some way, then that laser will take longer or shorter to get back. And then when it lines up with the other light, the peaks will actually be out of sync. And you'll, instead of getting nice bright light, you'll actually get bright light, dark light, black light, dark light, because the peaks and the troughs will line up and cancel each other out, essentially. And that's basically what it is. There's much more to it that we can't explain with your present level of physics, but they actually built one of these things that's miles long. The longer you build one of these things, the more sensitive it is. And they built actually 2 of them, and now they have like 8 of them. But they built 2 of them, and when they turned them on to test them, they immediately detected a big event. And by looking at different astronomy sources, different radio telescopes, they were able to determine that this big event that they immediately detected during their test was actually the collision of 2 black holes. They were able to confirm that using radio telescopes. Black holes are supermassive stars that have collapsed into a very tiny space, and they're so massive that they warp space and time around them, so that even light can't get away from them if it gets too close. Light actually follows the universe. The universe actually dips down into the black hole and gets sucked into the black hole, the universe and time itself. And light does too if it gets too close to it. That's why they're called black holes. But two of these black holes converge, and when 2 of them converge, they make a huge bump in the universe. And this bump propagates outward like a wave. So the universe actually distorts, and that distortion travels outward. And we detected one of those. And we actually have detected many since. We thought it would be a pretty rare event to see a big like gravitational event like this, but it turns out they're happening in the universe all the time. And we've detected them, and we've been able to confirm them with other radio telescopes and other things like this, other methods. And so that would suggest that gravity is a wave. That's the answer to that. That's a really long answer to your question. Right? That should have been a simple answer, but it's really kind of complex, because there's also evidence. Well, there's a suggestion from the theories that we've come up with about forces that it might also be due to a particle, because every one of the other forces in the universe that we know of also has a particle associated with it. Gravity is the only one that doesn't. We know about all the particles for the other forces. Turns out there's only 4 forces in the universe. But the other 3 forces in the universe all have a particle that is exchanged during the force interaction. And so we assume that gravity does too, but we've never been able to detect it. But
Don't they call those gravitons? Like just the theory that gravity is associated with some sort of like particle?
That is correct. They do call them gravitons. The particle that is associated with the particles associated with the other 3 forces, the other 3, well, I think we actually talk about the 4 forces later on in this chapter. Maybe we don't. No, yeah, we do. Common forces? Maybe not. No, we don't. But anyway, the other 3 forces besides gravity are you have electromagnetic force, which accounts for most of the forces that we deal with on an everyday basis. Most of when you push on something, that's electromagnetic. Why? Because the electrons on the outside of your molecules and atoms and everything are interacting with the electrons on the outside of the molecules of whatever you're touching. And there's a repulsive force between those electrons, and that's electromagnetic, right? And the particles that's associated with electromagnetic forces is the photon. That is also the particle that is associated with light. So there's a relationship between electromagnetism, electricity, magnetism, and light, and contact, mass to mass contact, always has this kind of force, an electromagnetic force. And the electromagnetic force is one of the strongest forces in the universe. It's a very strong force. Gravity, it turns out, is the weakest force in the universe. And both of those forces actually act at a distance. Even when you're touching something, you're not actually touching it. The electric fields of your electrons are just pressing up against the electric fields of something else's electrons, right? And that's what that's all about. And chemistry deals entirely with electromagnetic forces. Chemistry has nothing to do with any other force, only the electromagnetic forces, because chemistry only deals with what is happening between the electrons, the valence electrons in particular, in an atom. And that's all it has to do with. That's all chemistry is. Yes, sir.
So, like you said, you don't actually touch things.
Yep.
So, why is a knife cutting?
So, and that's a really good question. A knife has a very, very tiny edge to it that has far fewer atoms across there than, like your hand or something. But they're on this knife edge, and so that their electrons are actually really close together. Their when that happens, when you have a sharp edge on anything, but particularly on metals, you get a lot of electrons at that edge. So the electric field at the edge of a knife is really a lot stronger than the electric field in your hand, and it can actually part the electric field in your hand. It'll actually push the electric field in your hand apart, and that's what causes it to cut your hand at a atomic level. So it is still electric fields. I mean, that's how anything is dismantled. Anything that's made of molecules and atoms is dismantled by dismantling or separating the electric fields, by pushing the electrons apart. And that's what knives do. So, good question. That's also why knives are made of metal, because that effect is much more prevalent with metals than it is with other materials. Obsidian is different, and obsidian can be very sharp per se, right? But and it's the same effect, right? But it's not nearly as sharp as metals can become. So nobody makes anything out of obsidian anymore, because it's just not as good as, say, steel. Steel can be sharpened much better than obsidian can. So, same with other things like other stones and other things like that. But yeah. Because of this crystalline structure. And the crystalline structure is similar to the structure of metals, and that's why they can both be sharpened. That's why they can both be sharp. But it's just not, the electrons don't move around on obsidian like they do in metals to make this even better. So it's interesting, but it's true. The atomic level. So anyway, that didn't get us very far in this chapter, but we did talk a lot about forces, which is important. We are going to, let's finish up this section really quick. Here we have an interesting situation where we have a handle connected to a spring, and we have a block here of something really heavy, or maybe it's just a wall that's connected to a wall. And you pull on the spring. What do you notice? The harder you pull on the spring, what happens? Is it easier to pull it harder and harder, or does it get harder as you pull it more?
It gets more difficult.
Yeah, it gets
the
more
further you get.
So this is a variable force. A spring provides a variable force, and anything that's springy, in fact, just about any material, even if it's not springy, has this kind of reaction force. If you try to pull on a rubber band and you pull it 1 inch and then you pull it 2 inches, it gets twice as hard to pull. And it's true for steel, it's true for rubber, it's true for plastic, it's true for glass, and it's true for even the material these tables made of, which is some kind of epoxy polymer thing. Everything bends and everything stretches and everything compresses at least a little bit. And that stretchy compressiness gets harder it pulls back harder the more you pull on it or the more you push on it. And this is what is called a restoring force. You're trying to pull the atoms apart and they're trying to pull themselves back together, right? So that's again back to the electromagnetic force. but it's a restoring force. It's trying to go back to where it was. And it's always in the opposite direction that you try to force it to go. If you try to pull it apart, it tries to pull itself back together. If you try to squish it together, it tries to push itself back apart. And this is a very common type of force in the world today, the restoring force. We actually take advantage of it in many cases to measure weight or to measure forces or other things. Here's an interesting thing to talk about, which is the forces on an object when it's in contact with something else. We have a person sitting on a chair and his weight is pulling him down into the chair, but he's not actually moving, he's sitting there. So there's another force from the chair pushing on him. Gravity is pulling him down, the chair is pushing him up, and those two forces are going to cancel because they're equal and opposite, it turns out. And he's not going to go anywhere. Those forces are not going to result in anything happening. Right? In fact, this is actually what our weight is. When we feel our weight, we're not feeling gravity pulling us down, we're feeling the earth pushing us up. That's what we feel when we feel our weight. And that's why we feel heavier when we're in an elevator and the elevator is pushing us up even more than gravity. Well, even more than the ground pushes us up when the gravity pulls us down. You feel heavier when the elevator goes up. And what happens when the elevator goes down? You feel lighter because the ground is falling out from beneath you and you don't feel as much force pushing on your feet. You feel your weight in your feet. That's why your feet get tired at the end of a long day standing. So we know about how vectors work. Force vectors work the same way velocity vectors work and everything else. We don't need to do anything differently there. And we will get on to the laws of Newton on Wednesday and get you more into the homework.
I guess I have one more question.
Yep.
Just for the sake of it. So you mentioned gravity, like moving in waves, but like it takes time for things that are further away to like the force to act on anything else.
Yep.
I guess. So is it possible for like you had said, there's something far, far away and it takes a while for the gravity to affect us. Is it possible to be affected by the gravity of something that's just no longer there? Kind of like how light is.
Yes, because the gravity from an event can, so you can have an event that's very far away that can happen, and then that gravitational wave travels through space and maybe takes 1 million years to get somewhere else. And in that intervening million years, the thing that caused that gravity can have moved on to become something else or whatever else. Yes, for sure, it can. The thing that caused it can change or move in the intervening time. But that's why Einstein said that time is actually just part of space, because that all that really has to do with is the distance between the two events. The one event is the gravitational event. The other event is you observing the gravitational event. And the only thing that really defines anything is the distance between them, not because time is something that was invented by human beings when we saw the sun rise, which of course the sun doesn't rise, the earth rotates, right?
Yeah.
So we invented it to explain the things around us, and we're so tied to it that we can't imagine a universe without it. Even really well-known physicists that have a lot of understanding of the universe many of them don't believe Einstein. Many of them don't believe that time really is just a part of space. And so they come up with this idea of the space-time continuum, where time is part of space, but not part of space. And it's kind of its own thing, but kind of related to space. I'm not an adherent of that belief, but it's very difficult to divorce ourselves from time. It's such a part of our human understanding. So.
Makes sense.
Anything else?
All right. No, I think that's it.
All right. Have a good one.
You too. Thank you.
Yep. See you.